Okay, now we discuss about the case when we plug the string at 1/4 part, means when string is plugged at quarter length. Let's again we consider a string of length L clamped between two fixed points, and this string having tension T and mass per unit length M, and the mass of that string is capital M. Now, when we plug that string at the 1/4 part, then at that side there is formation of one complete wave, along with there is formation of a pulse. On other side there is just formation of one pulse. Now these two waves, means here one complete wave and one pulse, and one dead pulse and pulse generated other side, they both together these waves together form a two complete waves, one complete wave and one pulse at that side and other pulse at that side. So there is formation of two complete waves. So when these waves move towards two opposite sides, one move at that side and other move at that side, after reflection from clamped ends, these waves meet at certain point, and after meeting we mean that after superposition of these waves there is formation of two stationary waves, means now this whole string of length L vibrate in two loops when we plugged it at a 1/4 length or 1/4 length. Now this whole string vibrate in two loops, means here we have three nodes. The points where particles of the medium, means particle of the string, are at rest, these points we call the nodes. So there are three nodes and there are formation of two antinodes, the points where particles are at maximum amplitude, these points we call the antinode. Now we know that the distance between two nodes, consecutive nodes, is lambda by 2, and the distance between these two nodes is also lambda by 2. Here we discuss the second case, so we write this is our second wavelength lambda 2. Distance is lambda 2 by 2 and this distance is also lambda 2 by 2. So if we write the expression for length of this string, then this length of the string denoted by L equal to lambda 2 by 2 plus lambda 2 by 2. By adding, we can write that L is equal to 2 lambda 2 divided by 2. Half lambda 2, lambda 2 by 2, 1 lambda 2 by 2 and plus 1 lambda by 2. We have 2 lambda 2 divided by 2. Or we can write L is equal to lambda 2. So if we write the expression of the wavelength, we can write that lambda 2 is equal to 2L divided by 2, or this 2 is cancelled with this one. We have second wavelength lambda 2 is equal to length, or lambda 2 is equal to 2L divided by 2. This 2 multiply with L and this 2 divided by L. So we have expression for second wavelength that lambda 2 is equal to 2L by 2. Now again we write the expression of the speed of the transverse waves, that V is equal to F lambda. For second case we write frequency F2 and wavelength lambda 2, and for expression of frequency we can write F2 is equal to V divided by lambda 2. Here we have value of lambda 2, that 2L divided by 2. So instead of lambda 2 we write the value F2 is equal to V divided by 2L divided by 2. Or we can write this 2 is on third place, so we can write it on first place. We have expression that F2 is equal to 2V divided by 2L. As we write the expression for fundamental frequency that F1 is equal to V divided by 2L. So we can write this expression in terms of fundamental frequency or first harmonic, that F2 is equal to 2 into V divided by 2L. This V divided by 2L is the fundamental frequency F1. So we can write frequency F2 is equal to 2 times F1. We also write the expression for fundamental frequency F1 by putting the value of the speed of transverse stationary waves, that V is equal to under root T divided by small m mass per unit length. After putting the value of V, we get the expression for fundamental frequency, that F1 is equal to 1 divided by 2L under root T by m. So instead of F1, we can also write that F2 is equal to 2 times 1 by 2L under root T by m. This is the value of the fundamental frequency when we replace this V with its value. This 2 is cancelled with this one, so we have second frequency F2 is equal to 1 by L under root T by m. This expression that F2 is equal to 2 times F1 show that when loop moves in two stationary waves, when this string moves in two loops or this formation of two stationary waves, then the frequency of these waves we call the second harmonic frequency, and this second harmonic frequency is double of the first harmonic frequency. It's 2 times the first harmonic frequency. That frequency we also call the fundamental frequency. So when when string moves in two loops, then the frequency of the string is double of the string frequency when it's moved in a single loop, and that frequency we call the fundamental frequency, or we called it a first harmonic frequency. Second harmonic frequency is double of first harmonic frequency.